Hi everyone, today we're going to talk about pH of weak bases and Ka-Kb relationship. What is a weak base? It reacts with water to form hydroxide ion. So water must be shown in the acid-base equation, such as B reacting with water, and water is donating the proton to form BH plus, the conjugate acid of B, and then water becomes the hydroxide ion, which is the conjugate base of water. Now here's a number of weak bases, typically ammonia, methylamine, ethylamine, aniline, and pyridine, all with their Kb values. And that can be used in our calculations later. Practice problem number 1. Calculate the hydroxide ion concentration POH and pH of a 0.15 molar ammonia solution. First, we write the equation ammonia in water to form ammonium and hydroxide ions. And then we attached the concentration at equilibrium. With ammonia is 0.15 molar minus X, and with ammonium and hydroxide ions are X molarity formed. The formation of hydroxide ion dictates the use of Kb in our calculation, so Kb is set up as product over reactant concentration without the water liquid in there. So 1.8 times 10 to the minus 5 is equal to x squared over 0.15 minus x. Now we can assume the x is very small and negligible, which can be dropped from the denominator. Solving for x, the hydroxide ion concentration is 1.6 times 10 to the minus 3 molar. Therefore, the pOH is equal to 2.80. And the pH can be calculated by subtracting pOH from 14.00 to obtain 11.20. Let's examine the relationship between Ka and Kb. Look at ammonia. With ammonium ion, they are a conjugate acid-base pair. Now for the base ammonia, to ionize in water forming ammonium and hydroxide ion, the Kb value is 1.8 times 10 to the minus 5. Now we take the conjugate acid, the ammonium ion, and ionize in water to form the hydrogen ion and ammonia, and Ka value is 5.6 times 10 to the minus 10. Now if we add up the two equations, we can cancel out the ammonia and the ammonium ion on both sides of the arrow. We end up having the ionization of water to form hydrogen ion and hydroxide ion. Remember from the equilibrium unit that when we add up two equations, we multiply the K values together. So now we have Ka times Kb, which is equal to Kw, the ion product of water. Now, we can then take a negative log of Ka plus the negative log of Kb equal to negative log of Kw. This is equal to pKa plus pKb equal to pKw, which is 14.00 at room temperature. Now we have derived a new formula to use. We can also calculate Ka if we know what Kb is through the relationship with Kw. So Kw over Kb will give us Ka. When do we need to find Ka? When a hydronium ion is formed in the ionization. We can also calculate Kb by dividing Kw by Ka. And when do we need to use Kb? Whenever hydroxide ion is formed in the ionization. When the Ka is greater than Kb, that means the Ka for the conjugate acid is greater than the Kb of the base, solution is acidic. The reverse, when Kb is greater than Ka, then the solution is basic. Try practice problem number 2. What is the conjugate acid of cyanide ion? And we know the conjugate acid, we have to add a proton to it, so it is HCN, hydrocyanic acid. Given the Kb of cyanide ion is 1.6 times 10 to the minus 5, what is Ka? Remember K is equal to Kw over Kb, so this is 1.0 times 10 to the minus 14 over 1.6 times 10 to the minus 5. And we have 6.3 times 10 to the negative 10 for the Ka value. Which is stronger, the base or the conjugate acid? Now here we have to compare the Kb with the Ka value. Since Kb is greater than Ka, we say the base sign Cn minus ion is stronger than the conjugate acid HCN. Practice problem number 3. I have a 0.5 molar Kf solution with a pH of 8.42. Determine the Kb for the F minus ion and Ka value for HF. When we write the hydrolysis of the salt in a net ionic equation, we can eliminate the K plus ion, which is spectator ion, now with the F minus in water forming HF and OH minus. The POH is equal to 14 minus pH, which is 5.58. From that, we can then take the anti-log and find the hydroxide ion concentration being 2.6 times 10 to the negative 6 molar. Now then we set up the Kb expression, which is HF times hydroxide ion over F minus ion. Since the HF and OH minus have the same concentration, it's 2.6 times 10 to the negative 6 raised to the power 2 over the fluoride ion concentration from the Kf, which is 0.5. We then calculate it to be 1.4 times 10 to the negative 11. And then from that, we can derive Ka by taking Kw over Kb, and we end up with 7.0 times 10 to the negative 4 being Ka value. To summarize what we have learned today, we have learned what the common weak bases are, and we learned how to calculate the pH of a weak base. We further explore the relationship between Ka and Kb for a conjugate acid-base pair. And then we use Ka and Kb values to determine the relative strength of a conjugate acid-base pair. I hope that you find this video helpful to you. From the team of MLCA, we'd like to thank you for watching our video and hope to see you again soon.